welcome to DevOps Belfast at the NIDC Meetup week. Very nice to see us here. It's nice to get out in person again rather than our meetups online for the last 18 months or so. So thanks very much for coming along, and thanks for those who are watching on YouTube. We have two speakers tonight. We have Chris Laughlin who's going to do a lightning talk first. And then we have Jonathan McDowell who's going to do a longer talk after that. So with that, Chris, if you're ready, we'll get going, and we'll see you at the end. There's the awkward silence when I stand here and make sure my Mac works. Isn't it great when technology works? And when I talk loud enough in the mic, let me know. I don't know. Is it? Oh, okay, cool. You can hear me? Sweet, if you can. So, I'm Chris Laughlin. I'm here to talk about how to build and ship anywhere. Get the whole introduction thing out of the way. I'm Chris Laughlin. I'm a principal UI engineer at Rapid7. I don't have hobbies or interests, so I spend all my spare time writing code and trying to figure out problems for solutions and solutions for problems that probably didn't exist, that don't need to be solved. So today I'm going to take you on a little journey. Hopefully it's interesting, you have some takeaways from it. If not, it just makes me look really vain and want to talk about myself and what I did. But sure, we'll see how it goes without the talk. So with every good journey, there's always a beginning. So it's kind of like step back to the beginning. A couple of years ago, I really got into making side projects, building web applications on my own, but I wanted to kind of keep it going and growing, but I ran into one of the main problems. I had a MacBook, like everyone in this room probably has a MacBook they use for their work, or a really high-spec Windows laptop, well, I'll not discriminate. But it was my work MacBook, and I don't want to mix work and personal things. As much as I have a lot of personal repos on my MacBook, I shouldn't be using work equipment for personal stuff. So I kind of thought to myself, right, I really want to get into doing this personal work, but I don't have 2,000 quid spare to buy a MacBook to do my own things. And the majority of the time as well, this 2,000 quid machine would be for watching YouTube 90% of the time, and 10% of the time would be actually writing code and doing things. So I kind of went on the hunt of what can I do, how can I resource a development environment that will meet my budget and meet my needs. And I kind of dug around a bit and kind of came across a Chromebook. So I got a Chromebook from my ma the year beforehand, because you can't get a virus in a Chromebook and you don't have to update things, and it's safe for her to use in her days of technology. So this is great. It's 100 quid, perfect. It's portable, it's light. And I always like the ads for Chromebooks where you could be typing on a document and you'd smash a keyboard in half and they'd hand you a new one, and you just keep going like nothing ever happened. Although the one big caveat is a Chromebook is just a glorified Chrome browser in the shell of a laptop. Granted, the ones nowadays you can actually install Android apps and that kind of stuff on them, but the one I got was really cheap and old. So I kind of thought to myself, right, well, I want to build sophisticated web apps, I want to deploy them, I want to do it from anywhere, but all I have is a Chrome browser. So what can I do to kind of build applications without the constraints, without this shiny metal? I know, ironically, I'm talking with a MacBook in front of me, that is a work MacBook, without the shiny piece of metal that costs so much money. So I was right, I have a browser, I have the power of the web, as long as I have a connection, I can start building, I can start working and making applications. So the first thing I kind of jumped into was GitHub. So I'm making a personal website, I can go in the GitHub editor, I can click edit, I can start typing in, adding some, in this case, styles to my personal website. Could be a site for your dog, or some GeoCities style thing that you build in the day. Now this is kind of cool. We can start typing in. It auto tab there for me. That was kind of nice. I can add a body, and then I can paste in some code that I copied from Stack Overflow. But it's really badly looking. There's no syntax highlighting. But I can commit directly to the repo. And GitHub will rebuild that site. Now that's not the rebuild version, obviously, but GitHub will rebuild that site and handle everything for me. So this is kind of cool. This is a starting, this could be a personal blog, it could be a website for my dog, whatever we want to do. So what are the pros here? It's simple. I don't have to think too much about it. I just type, commit. If I know how to use Git and I can type, then I can do this. It's quick, a minute or two between each refresh building this. So I'm now kind of getting the point where I'm building an application or a site or some sort of user-facing product that I can use. I can commit and forget. So let's take a blog example. I can add a new blog, commit, walk away. It'll be there for whoever wants to see it. The obvious cons that come from this: there's no syntax highlighting. I have to know where that closing tag came from, or I have to see pretty colors in my editor. There's no error handling. That could have been broken code that I just shipped out to a production application. There's nothing stopping me putting any checks in places. And it's a single file edit, and I don't really like that. I want to edit or add multiple files in one commit and gather them together, like you should do, and then give it a really meaningful commit message like updating. So I kind of thought, right, where can I go from here? What's the next level? Like, how can I build an application in the browser with no hardware, no installed apps? So I kind of came across Code Sandbox. So Code Sandbox is a really cool environment. I'm able to grab the Git URL, fire it in the Code Sandbox. You can see here, add it in, and import it. So now I've taken a repo, and I've put it into an online IDE. So we're kind of getting a little bit further. If I go on the next example, so here we have our editor. We've got our syntax highlighting. We can then add new files, so now I can do multi-file. We get a live preview of the application, so I can debug as I'm developing. I can find problems, I can see what's going on. And it's all, again, in the browser. There's some nice auto-completion. It's telling me when I'm writing things that are wrong, which is 90% of the time. So I'm kind of building up this ability, take this portable development environment wherever I want to go. And here I'm just creating a React application with a component. It could be anything. I can also tap into the ecosystem of my web application, using npm scripts, adding dependencies. So, okay, we're kind of getting a little bit further. We're making a bit more progress. So what are the pros of this? I got my syntax highlighted, I can see the closing tag or something, I can see what's going wrong. I get my auto-completion, so I have to type everything out manually. Again, the multi-file edit, so I can add multiple files, I can do whatever I want to do. And the live preview is the strongest thing. I can see exactly what I'm developing, and I can see the output of that. With everything, there's pros, there's cons, obviously. I think for me, is I'm removed myself from GitHub, so I'm not connected to the source anymore. GitHub was at the one-stop shop. I could do everything in that one environment. As well as a limited running capability. I can run that application, but I don't have a terminal, I don't have anything. It's not a fully fledged IDE. It's not like I'm using, WebStorm on a MacBook where I can develop and run everything. I can run tests and stuff like that, but it's still limited in the capabilities of what it provides me. But we're getting further and we're getting further. So I keep on using this, I keep on building on it, and I'm waiting to see what are the new advancements and changes that are coming out. So we step a little bit further until nowadays times. By hitting the dot key on any GitHub repo, it'll bring up a virtual browser-based VS Code instance. So if I'm using VS Code in my day-to-day on my expensive MacBook that the fans explode, I now have this in the browser. It's not exploding. I can start editing. I can do whatever I need to do. I can pull in my themes. I can pull in my plugins. I can start using the tools I'm familiar with and used to day in and day out as I build my application. You're going through, you're adding files. It's a very similar experience. A little bit more connected to GitHub than it was from the Code Sandbox idea. Code Sandbox is connected, but you can easily break the connections, and trying to port a repo back in to GitHub from Sandbox is very difficult. Now this could be because I'm using the free version and I'm cheap and not paying for it, but it seems to be very unreliable. So again, let's look at the pros and cons of this. So it's a familiar environment. I'm used to using VS Code. I can import my plugins, I can import my syntax. I can share the themes. It's connected to GitHub. I just hit that one key. I know I can edit a repo, I can manage it, I can work with it. Again, we hit some cons. There's no live preview. We've lost that live preview. It is on the way, and there's different ways you can do it, but for the simple browser-based example, you still need to install something for it. The last one's it's a con, but a pro, depending on how you think about it. It's still in early development. They're still making changes and adding new features, which is a con because I'm limited in what I can do at the moment, but it's a pro in the fact that if I stick with this, they're going to add more and more features. So we've kind of got to this point now where we have this browser-based ID. I can develop any type of code for any type of repo, anywhere I want to go. This is great. We can edit stuff, we can commit it to Git, but the second part of the talk was shipping as well. So how can we then turn this into some sort of shipping mechanism that I can use and take anywhere? My flavor of choice is Netlify. You can use Vercel or other tools out there as well. But with Netlify, I find it very handy. Like, this is the dashboard. I link it to my GitHub account. It automatically pulls in all my repos. I find the repo that I want to use. I click on it. It analyzes that repo, determines what type of project it is. Says, this is a Create React app project. I know how to build it and ship it. I click one button and it starts running. For the time it takes to run npm install and npm build, it's published it. And it's gone out to its network of CDNs, it's handling caching, it's handling auto-scaling. They have the ability as well to do serverless functions, capture form data, but I don't need to think about it. I've never yet installed anything native to my machine. Everything's just still in the browser, still free, still easy. I can smash the Chromebook in half and get a new one and still work away. So I'm kind of at this point now where I am building and shipping from anywhere. But with Netlify as well, what comes into play is like we get the GitHub integration. So now we've also built a CI/CD pipeline into the play. So every time I raise a PR, it builds it, creates a branch, publishes that as the real application. So even if I don't have that live preview, I can create a PR, view it in the live preview, fix my bugs, go back again, change it, it'll rebuild it for me. So I've kind of built this whole cycle, all in the cloud, no native apps. I can build, CI/CD, ship. So now we can throw up our hands and say we don't need these 2,000 quid machines sitting on our desk. The fans are getting really hot because we're opening one instance of Chrome. And on that note as well, the Chromebook never got warm, weirdly enough. I don't know why. Maybe it's something to do with Apple and Chrome. But we've taken that point where we can now build an application, edit the application, test it, go through a pipeline, deploy it from anywhere we want, whether we're working at home, working in the office, or working at the top of the moors, as long as you have an internet connection up there. I don't know, maybe 4G is up there, I'm not too sure. That was a very lightning talk, quick talk, but thank you very much. Any questions?
I've actually got a quick question. Just on the DevOps side of things, Netlify basically triggers from GitHub, so it's got its own CI/CD running at its end. Whereas if you've got something like static web apps, or I think AWS Amplify as well, then they do it via actual GitHub actions. So it's GitHub pushes it to the service rather than the service doing everything itself. Do you have any thoughts on which you prefer of those?
I kind of prefer the Netlify way because I just say, here's the repo, build it for me. Every time I merge into master, it automatically rebuilds, or every time I create a PR, it automatically rebuilds. On the other side, I'd have to configure GitHub Actions. I'd have to know how to write a YAML file and figure out how to configure the things where I really want this, I just click a couple of buttons and it's done. I can spend the time writing the code and building the application and not worrying about how it's being deployed or how it's being managed and understood.
Thank you.
Thank you. Now, they're good, and we probably should use them more, but there's that ever-increasing level of abstraction of, I have no idea what's actually happening now. Does that bother you? Sorry, it bothers me. I don't know whether it should, but it does.
So I totally agree, because I work in a company where we manage our AWS instance to a fine art, and we control how everything is working because we need to make sure our costs are this way, or we're deploying it that way in multiple regions. And I think each case is for what you're actually building. I see the likes of this pattern of using Netlify or these kind of providers, you're building like a market insight or a CMS that is targeting customers. Where if you're building an application where you need to control your scale and control how it grows, then you're going to go for the more fine-tuned like Azure or AWS. Where these ones are, I'm more concerned about how the product is built, the code that's going into it, and less about the actual deployment. Where, like for me as like a hobbyist, when I'm building all these things, I don't want to have to control how things scale or how things are going to be priced, and they just do the caching for me. Like I'm terrible at that kind of, did I configure this way, did I turn this up or did I turn that down? Am I going to like over scale for a blog that gets 10 users, like a month kind of thing? Awesome, thank you very much. Well, I like them to myself.
So thanks very much, Chris. So the second speaker tonight we have Jonathan McDowell. He's going to give a talk on let's talk about disks. So.
Work laptop, Linux, not Windows. But we Linux users really appreciate the good work you Mac users have done in convincing the world that it's not just Windows, so I'll be enough to It works. Does this work? Yes. Okay. Disks as libraries. This is a very much the opposite end of the spectrum talk. I'm going to talk about low-level stuff rather than things that are high-level. This is a rough overview. I'm a software person. I like to say that I know enough about hardware to annoy the hardware folks. I've spent mumble years building storage products. I don't want to get into how long. I'm not a librarian, but I'm going to use libraries as an analogy for disks throughout this entire talk. This was a conversation that started over a bottle of wine and dinner to try and explain to my wife what it is I do. But I have equally the same problems talking to other software engineers about what it is I do, because I build storage that's sort of very much at the bottom level of things. So it's a very selfish talk, right? This is all about me and trying to explain what I do so that people understand and I have conversations about stuff. All comments and opinions my own, not representing anyone else here. I do work for a storage company that has a Belfast office. We're not currently hiring, but I expect that to change next year. So hopefully this encourages some people that storage is a thing they might be interested in. But mostly it's about me taking pictures of libraries off the internet and making a talk out of it. This is someone's home library. This is their reading room in their house, and I'm like insanely jealous about this. It's obviously very filtered and everything, but it's like I want a room like this in my house. This is about block storage. So if you think about S3 is object storage. Here's an object, I go and put it somewhere and I get it back. What we have underneath that and on our laptops and on our servers is file storage. Here's a file, I want to read the contents of this file, I want to store my program as a file. All of that sits on top of block storage, so that's actually fixed size blocks that are addressed that represent space on a disk, but it's all fixed size. Traditionally, that's 512 bytes. I don't know why. These days we've got a bit bigger, and sometimes they're 4K or larger, especially with flash drives coming in. I'll talk a little bit about file systems at the end, just to sort of give you an idea about how that sort of ties in, but file systems are a complete talk in and of themselves. I'm old, I've been doing storage for a long time. The first hard drive I actually had, I don't think it was an ST506, but it was a full height 5¼ inch hard drive with about 10 megs capacity. These were incredibly dumb drives. They got two connections to them, one of which is sort of the control connection of saying which bit of the drive to access, and the other of which, as far as I understand, is actually the analog output roughly of what's coming off the head of the drive. The controller card dealt with like the encoding of what was going on and off this magnetic medium. So yeah, the drive's very dumb. The controller's not much smarter. The computers actually go and move to what they got is cylinders, heads and sectors. So multiple platters within the drive. Each side of the platter is a different head. So if you have two platters, you'll have potentially 4 heads. Cylinders are the rings in and out, and then along each ring you've got sectors alongside it. But the computer would actually go, read me this head, seek to this sector, tell me this, or seek to this cylinder, tell me the sector that comes off it. So really very involved in terms of how you did that. And I like to think of that as a little bit like a library. See, I told you the library's going to be involved. Think about the floor of the library, the shelf within the floor, and then the book position on that shelf, right? That's your heads is your floor, your cylinders is your shelf, and then your sector is the position on the thing. So what I'm going and doing is, all of my books are the same size as the artistic license I'm using here, but if I know where my book's located, I can go and pick it up off the shelf, right? I go to the right floor, I walk into the library, I go to the right floor, I walk along the shelf to the right shelf, I walk along and I find the book and I pull it out. The other artistic license here is that I get a copy of the book, right? There's another book in there, so I can, as many people as want can have the same book checked out rather than thing. But if I write a new book, if I put a new book back in that position, then everyone gets that new book. That slight tweak there, but effectively that's what you're doing, right? You're storing information. You've got fixed size of information. You have a location where that information lives, which is type of thing. But in this case, you know, old library, I go in and do it myself. It's very much a manual process. All that happens. We move to IDE. The IDE stands for Integrated Drive Electronics and does exactly what it says in the tin. So instead of that controller card, which gets the analog signal and sends all the data signals, IDE moves all of that to the drive itself. So sort of this connector is a 40-pin connector, and it's got, I think, 16 data bits on it and reads the data in and out. We've still got something that looks to software, like the ST506. So initial IDE is still very much a case of tell me, you know, which floor I want to be on, tell me which shelf I want to look at, tell me what sector it is. But really, if you think about it, what we've got is a situation where we've got a librarian, right? So I go to the library front desk, and the librarian goes down into the stacks and gets me my book, but I need to tell them exactly where that book is. So we've offloaded some of the work onto the disk or the library, but we're still very much using the same terminology to actually go and find the item. It's a case of go get me the piece of data from this shelf, the book in the library. Again, I told you there was going to be pictures of libraries. It makes for, I don't have any cats, I've got libraries. Library of Alexandria, famous, lots of scrolls. But up to, so you can see also that we've moved from 3,000 tablets, which they reckon were about 10,000 unique works, and we're now at up to 400,000 scrolls. Somewhere between 40 and 400,000 scrolls. They're not quite sure. I'm not sure how you can have such an order of difference in knowing what it is. But IDE was equally a huge leap on from the original ST506 stuff. More progress, right? So we have now got a librarian, right? So what we're doing is we're saying, hey, librarian, give me the book or whatever, you know, floor, shelf, position on the shelf. Drives are starting to get very big. In particular in the disk world, there was a certain number of bits for the head, the sector, and the cylinder. It started to be the drives were big enough that they were having to do some sort of level of remapping. Like the head field, I think, allowed for something like at least 16 heads, and many drives were maybe sitting with only 4. So what they did was pretend the drive had 16 heads because they couldn't fit all of the cylinders in. So it's sort of like kludging this about. So suddenly your cylinder head sector mapping is not actually a one-to-one mapping anymore. You're doing some level of translation. And once you start to get into that level of translation, well, you could do a completely different translation, right? If I'm going to a library and I don't get to talk to the data directly, I don't need to do it, the librarian's getting it for me. I don't care how they map the address I give them to where the book is. All I care about is that I know how to map, how to get the book I want. Think, for example, of the shelf breaks, right? They put a lot of heavy books on the shelf in a break, so what they do is they relocate all of those books to another shelf elsewhere. They can transparently do that themselves, and I talk to the address that it used to be at, and they know how to do the mapping in the back end. This is equivalent to disks doing bad block remapping, right? So if a disk detects that a particular area is going bad, or a flash sector is wearing out in a modern SSD, it can remap to a good area drive and transparently update its internal mapping tables, because what it now has is a logical block address, and you don't care what actual cylinder head and sector that's on anymore, or which particular flash chip it ends up on. All you care about is I access location 1, I get back what I put in location 1. And from a library point of view, I mean, you've got the librarian in the way, they can do this translation for you. So we get into this stage now where all of a sudden we've abstracted out, I have a single idea of where my data is, I don't really care physically where that is. We've moved slightly more up the abstraction layer. SCSI was already doing this. SCSI is sort of a much smarter protocol than the likes of IDE and ATA were. And then sort of ATA made it much more common, which is sort of like the second generation of IDE drives. And we're still in this sort of 40-pin connector. We haven't moved into SATA, even though SATA looks a lot like this from the protocol layer. We're still in sort of the early days. So once we've got logical block addressing, really what we're down to is disks are all about reads and writes. They are incredibly simple things in terms of what you're actually doing with them. Fundamentally, this is the SCSI read 10 command and the SCSI write 10 command, and you can build most of what you all do with disks with just these 2 commands. And what happens is the left one says, read me some data. Nope. So the LBA is 4 bytes in this. There's a length and there's some miscellaneous control fields, and it basically says, read me the data off this LBA. And the alternative is the write, which says, write this data to this LBA, your data will go along to it. Ultimately, under the hood of most storage devices you're using these days, this is roughly what's happening. NVMe's got a slightly different command set, but same principles. SD cards, doing something akin to this. USB sticks, doing something akin to this. SCSI disks, doing something akin to this. SAS drives, doing something akin to this. SATA drives, doing something akin to this. Basic principles. The only reason it gets complicated is you might have thousands or hundreds of thousands of these in flight in any 1 second, right? Modern SSDs, I think I saw the other day, Linux has managed to get 8 million IOPS, IO operations per second, on a single CPU core, right? I mean, I remember hard drives having sort of like 100 to 200 IOPS. I think that a modern SSD can maybe hit somewhere between 10 and 100,000 KIOPS a second, and very modern ones can get much faster. So it's a sheer volume of concurrency going on that is really where the complexity comes from this. But ultimately, at the end of the day, your file system, your object storage are doing these very, very basic block-based operations under the hood. So we've got a bunch of very simple primitives here, reads and writes. We've got them using LBAs. We've sort of abstracted out what's happening with the drive underneath. Now we can do some interesting stuff with it. Well, interesting if you're a sad storage geek, but trust me, it's kind of cool, some of the stuff you can do. Tied command queuing, native command queuing sometimes. We talked about a single command at a time. I said there now that we could do multiple IOPS in a set, thousands, tens of thousands. What I can do is submit multiple commands at once, right? Once I get a bit smarter in the drive, instead of saying go and read location 1, go and read location 2, go and read location 3, or more likely go and read location 1 while another application wants location 1000 and then another application wants location 500, I can submit all 3 requests at the same time, and the drive can do what it thinks best, right? So in the old days of rotating media, I might well find that the drive reordered the commands because the head passed a particular piece of data, and it knew that it could pick that up. It's like, hey, you've asked for 1,500. I'm actually going to go past 500 on my way to 1,000, so I'll pick it up along the way and complete it faster. It'll be a more efficient operation. Or it might just be some operations take longer than others, and I can complete, say, a read operation much faster than the operation of writing some data to the SSD. You give the drive the choice to then run multiple things in parallel by having this sort of tight command queuing, and I think SATA does a queue depth of about 32 at a time. SCSI has this ability to do lots and lots and lots, but most drives don't support lots and lots and lots. So this suddenly says I've turned up to the library, and instead of there being one librarian, there are 32 librarians which I can submit requests to, and they'll go and do things. Or one librarian I can give 32 commands to, who'll go off and try and do them. And again, as I say, the drive gets to do some reordering of that and be a bit more efficient about it. I don't know where this library is, I just kind of like the picture. RAID, redundant array of inexpensive disks. Software versus hardware. Ultimately, what you're trying to do with RAID is present something that looks like a single hard drive to the upper layers. So what I'm saying is these read and write commands are coming in from the software layer, and I'm acknowledging them as if I was a drive, right? And the idea is, for example, RAID 1 is the most common or easiest to explain. I have 2 libraries, and I store a copy of every book at the same location in both libraries, right? So if I'm software, I go to both librarians and give them a copy of the data and say, here, store this for me in location 1. Or if I have a piece of hardware doing it, what I do is I go to the hardware, and it looks like a librarian, and that then talks to the back end of the disk. It sort of provides this translation layer and invites it in. And then when I want the data back, I can pick which one I want to choose it back from, right? And in some ways, if you've got both drives, both libraries happy, you can split your requests out and spread them between them. So all of a sudden, if you've got 32 librarians on both sides, you can have 64 requests in flight because you can spread them out. But then when one side fails, you can go and ask the side you know is still alive for the data, right? Basic principle of RAID. One drive dies, you have somewhere you can ask for the data because you've stored 2 copies of it. There are complexities about parity and whatever for RAID 5, but RAID 1, nice and easy. 2 copies. You write twice, you only need to read once. If you want to be paranoid, you can do a read from both sides and do a comparison for checks. Hopefully everyone recognizes the Maclay library. I was trying to find a picture of 2 libraries side by side just so I could do this, but I couldn't find one that was easy. Compression. So lots of data we store is easily compressible. If I'm storing, let's say I'm a library and I have a librarian, I might shrink the book down, right? I might actually make a smaller copy of the book and sort of go, right, I can fit more words into this space because my equipment is good enough that you've written it in a children's book, right? And the text is very big, and I'm going to squeeze it down into sort of like, 8-point font. And what I'll do is when you ask for it again, I will print out a copy or copy it in a way with my photocopier that makes it big again, right? So the acuity of what I can put in is I can put in a smaller thing, and that way I can store more books in the space. But again, because I do that translation, because I'm the librarian standing between you and your data, I can do that translation layer. Now equally, all of these things that I talk about the librarian doing, you can do in software. We can do software level compression before it gets to the drive. It's a choice about whether you're using the capabilities of your storage equipment or whether or not you're using up CPU resource on the server itself or the computer itself. And again, this is something you can do at a file system level. And sometimes the file system level will then give you a little bit more knowledge because you've got the entire file and you can say, I want to compress, this multi-megabyte file rather than having to worry about it block by block. But you can actually get significant savings if you sort of aggregate the blocks up, especially once you get to the bigger block sizes like 4K. It starts to be worthwhile. and also you need the file system to support it, and not all of them do. Again, I'm sorry, I didn't keep a record of all the library pictures I found. It was just things I liked, pictures of books. Deduplication. Again, think about a server that's hosting a whole bunch of VMs. There's a lot of duplicated data there. You've got many copies of Linux or many copies of Windows. Let's think about whether or not I've got a copy of the complete works of Shakespeare and a copy of Hamlet. Obviously, Hamlet is contained within the complete works of Shakespeare, so what I could do is, where Hamlet goes, I can provide a pointer that says, hey, go and get the actual text from this location, right? And I'll go and get the point into what's in the complete works of Shakespeare. So rather than storing two identical copies of the data, I provide pointers to the data from other places. So let's say, in the case of a book, librarian is doing that arbitration, it can go and pick up that piece and copy that middle of a book and give you just that chunk of data. Modulo things like formatting and whether the pictures are right and the cover and all of those things. But the actual words in the middle are the same, it's the same text, so you can just store that pointer to it. And again, that's quite useful in the case of even containers, right? Modern workloads on servers have lots of data that is duplicated. Now you might have a file system that can do that for you as well. Again, all of these things can be done at higher levels, but even if you start out with a bunch of VMs where the golden image is all the same, they all do updates at different times, and you'll find they diverge unless you're keeping something at the storage level that's actually keeping them merged together again. Encryption at rest. This is kind of stupid, right? This is a thing that especially HIPAA get into in terms of secure storage of data. The principle is that the data on your drive should be encrypted, right? And you need a key to access it. And when you at a hardware level, what you do when you turn on the drive is you send the key to go, hey, I know the key, and that unlocks the drives, and it's cryptographically, it's like an AES key or something similar, and it means that if the drive is stolen, no one should be able to get the data off it without having that key. The problem is that this is inconvenient, so most people have drives in servers that the stuff on the boot drive of the server then has the key that unlocks the rest of the system, because otherwise you need someone to physically go and put the key in. So if they steal the entire server, they can still read all your data because the key's on another drive in that server, or it's stored in the TPM, or in some way they can get it. But the principle is, if I've got a bunch of hot swap drives in it and someone comes in and steals one of the hot swap drives, the key isn't in that drive itself, it's on something else, and therefore they can take it away, and it's a kind of requirement. But think about it as a way of the librarian just sort of throws books wherever they feel like it, and there's no way you can find that unless they've got their decryption key about how they actually map things together, right? It's about, I've taken the data and I've scrambled it, but you come in and give me the key, and that means I know how to unscramble it again whenever you come and get it, right? So it's about this. If anyone walked into the library, they wouldn't be able to figure out what data was what or read the data. They need that encryption key and the knowledge of the librarian in order to actually be able to get the data back out of it. It's a good way of doing things like security erasing SSDs, right? Most of the SSDs these days will do encryption at rest, and if you program a key into it and then your flash fails, the key isn't stored on the drive, so if the drive, you can just throw the drive away. You know, all this thing about destroying hard drives with hammers and making sure the data can't be found on it. If you've actually done an encryption on the entire drive with encryption at rest, it does mean you can throw away the hardware even when it fails, and no one will be able to read it off it. There are a few SSDs that have dodgy implementations of that, so you want to be a bit careful, but modern enterprise stuff is all good. I've raced through that. File systems. File systems are a way of sort of mapping many of those blocks together in a way that then means you can access them via something a bit more useful, like a file name. And think about file system as being metadata you put on the drive at a well-known location, right? So usually at the start of the drive, you put something that starts being your set of index cards, right? And it's in some sort of well-defined order, like alphabetical index cards. And I go through it and I find the index card from that bit at the start, and it then has an indication on it of what blocks I need to look at for the data. So it might have, for the complete works of Shakespeare, location 1, 2, 3, and 4, and maybe then for Hamlet it actually is the pointer to say just go to location 3 and pick it up from there. And that's kind of how that works. You can get into some very complicated things with file systems about dealing with failures or fast lookups or faster writes or whatever, but by and large it's about starting out with some data at a well-known location on the disk, and then that providing pointers to how you find the rest of the data. That is quicker than I expected to go through that, but I'm happy to answer questions. Yeah, so I primarily work on mirroring of data at a block level across networks. So it's kind of like network RAID level side of things. The company I work for produces a server-based storage product that then clusters the storage between your servers so that if one server fails, other servers have access to it, and I'm responsible for that sort of network layer.
Talk about the history over the last number of years. So where do you see the future going? Is it just more about speed? Because the amount of capacity of generated now and so on, the storage and that, where do you see
the really interesting one that has been really coming tomorrow on us for at least the last 10 years is the storage that is almost as fast as RAM. So if you look at, I mean, we've moved from spinning disks, right? Original ST506s were very slow. IDE got faster, SATA got faster. I mean, the SATA interface these days I think is 6 gigabits a second. I think SAS goes up to 12 gigabits a second. NVMe flash storage gets much faster, as well as being lower latency and more IOPS. You can easily saturate a PCIe bus on that, but the latency is still noticeably higher. Intel brought out Optane, what, about 4, 5, 6 years ago? I can't remember exactly when. And one of the things that didn't get trumpeted about Optane is that it's actually new physics. It's a thing called phase change memory. So although they tout Optane as being super fast flash, Optane is actually, if I remember correctly, phase change memory, and it's byte accessible rather than being block accessible. And the idea was always that it was going to be 10 times slower than DDR was where they were sort of pitching it at, and they were going to get it faster. And I think it ended up being at least an order of magnitude, if not 2 or 3 orders of magnitude slower than that. It's still significantly faster than Flash. One of the things they ship Optane for these days is as a caching layer for both hard drives and SSDs. But that's a really interesting space, right? HP spent a significant amount of time on a piece of research called The Machine, because they have a piece of technology they call Memristor, which again is one of these very fast changing storage, but permanent, right? So you turn the power off and it keeps storage. So it's as good as resilient like flash or hard drive, but it's supposed to be getting on for RAM access speeds. And what they did was they decided they were going to build a machine where RAM, instant access permanent memory, was the central concept of the machine, and they would build CPUs around it, but they would have terabytes of effectively storage. I think that's still sort of where we're going, right? We're getting faster and faster. At some point, some of the physics will come together about a different way of thinking about stuff. If you have terabytes of instantly accessible storage that retains power and is as fast as RAM, putting a file system on it is a waste, right? We can build an application in that always has its state, and you turn the computer off and you turn the computer back on, and you don't have to load anything from disk. It's already in memory, and that'll change the way we think about big data applications in a similar fashion to the way that we've changed a bunch of the way we think about storing data on disks with SSDs over hard drives. I don't think hard drives are going anywhere. I think that they're still managing to, physicists and chemists do amazing things with materials when it comes to hard drives. They squeeze all manner of little things on it, And I think we're still going to have that cold storage and media storage or whatever, but I think the really interesting one is when finally, and it's probably like Fusion, it's always 10 years out, but when finally we have this byte accessible, always available memory speed storage, it'll change the way we have to think about how we build applications. Well, it won't change the way we have to think about applications. There will be so much more ability open to us as a result. I'm very good at being a storage board.
More questions then? Well, thank you very much. And thanks very much also to Chris for his talk earlier. I'd also like to thank NIDC for hosting our DevOps Belfast meetup tonight. We are going to take, as DevOps Belfast, we normally take a break in December, so we'll not have anything. Hopefully in January we'll start up again. So we're always looking for talks. We're always looking for venues. So if anybody's got a flash new venue on Chichester Street or somewhere, I would like to host a meetup. Yeah, we're always looking for venues, always looking for speakers. So please let myself or Simon, who could make it here tonight, know, and we'll get that sorted. So again, thank you very much, and see you soon.